If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay student, welcome you all to this new lecture in machine series. So again we will be solving 5 questions starting from question number 156 to question number 160. Okay, then let's try to solve these 5 questions. In 156, the rotor of a 3-phase 5 kilowatt 400 volt 50 hertz slip ring induction motor is owned for 6 poles while its stator is owned for 4 poles. The approximate average no load speed at steady state when the motor is connected to this. So if the poles are different, so what happened in induction motor? So if you see the synchronous speed here, so stator is on for 4 poles, so your synchronous speed is 1500. Now at the starting your S is equal to 1, at starting your S is equal to 1. So rotor frequency also become 50. So if you see the rotor synchronous speed, it is 1000. So actually what happens in synchronous machine, both these rotating magnetic fields, they are running at same speed. What happens if your stator magnetic field, suppose it is running at 1500 rpm, so what happens in rotor, in case of rotor, the rotor itself rotates and its magnetic field also rotates. So suppose rotor itself rotates 1000 rpm and then its magnetic field will also rotate plus 500, so total rotation will be 1500. So ultimately this magnetic field and rotor magnetic field and stator magnetic field, they will look like stationary to each other. They will get locked. These two magnets will get locked and they will rotate. What happens? It is rotating 1500 rpm from its own, no physical rotation, because you have given polyphase supply, that's why it is rotating. Because you have given polyphase supply, it is rotating at 500 rpm, its magnetic field, but it is rotating on the top of a rotating wheel. That is, you are running inside a running train. So your speed increases, your original speed plus train speed get added. So that's it. It is rotating on the rotating rotor. So it is, this magnet is, you can think of it as running on a running train. So train will also has a speed and you are running inside that. So your speed will also get added. So that is something of this. But so what happens in the starting? Why it is rotor is this much? Because we generally keep this pole equal. Why? Because at the starting your S is 1. At the starting you just started this one. So you don't have any rotor magnetic field, that rotation doesn't comes. So because your S is 1, so whatever rotor rotates, that should, because at the starting your rotor rotation is 0, so this is 0, this 100 is 0, so the magnetic field rotation and this rotation should be equal, so that they can be locked each other. So as gradually what happens, as it starts picking up speeds, then this will come down because your sleep will then fall, so this frequency will fall. So at the very beginning, both these fields should have same synchronous speed, so that even if the rotor is not rotating, then also they can get locked. So once they get locked, then gradually if rotor starts rotating, then automatically that speed comes down. So you can think of initially both, this is 1500, this is stator MMF is rotating. So at the starting what happens? At the starting rotor MMF should also rotate at 1500 and rotor individual speed is 0 at the starting, so total is again 1500. Now what happens gradually your rotor MMF will reduce to 1500 to, it will come down suppose 200 and your rotor will take the rate speed, that is 1300, so total is 1500. It is rotor speed and it is rotor MMF on this rotor. So that happens. That's why this stator and rotor, the number of poles should be same. So that's why it will never start. That means its speed will be 0. So that is your answer. Now if you come to 157, no load test on a 3-phase induction motor was conducted at different supply voltage and plot of input power versus voltage is drawn. The curve was extrapolated to intersect the y-axis. The intersection point in y yields. So this is of this fashion. This is with volts and this is no load loss. Because no load power, so no load power means it will take care of all the losses. So what is happening in your copper loss? It is 0 because no load. So plus what are their iron loss plus friction and windows loss. So these are the total losses. So because it is no load, so whatever losses you are calculating, so that is having this plus this. Now this is voltage. Now if you bring this voltage to 0, not physically you are not bringing it 0. Physically if you bring it 0, then motor will be 0, no speed. But in graphically you are bringing it 0. Suppose it's given some voltage, because you cannot physically you cannot do it, because if you put V0, then there will be no rotation. You cannot measure the power. So you have taken the measurement something like this, suppose. Now if you bring it to 0, so theoretically what it is giving, because you are bringing it 0, so iron loss is going to also 0. So what is left is friction and windage loss. So it will intersect y-axis at a point which will give rise to a friction and windage loss only. You are extrapolating this one. You cannot do it physically. This graph you cannot do in lab physically. You cannot bring it here, because if you bring it here, motor will stop. If it stops, then how can you calculate your power? So you have done for some voltage to some voltage. Then you bring it graphically. You connect it. See the slope. Bring it to this one. Some method you use so that you can do the extrapolation. So theoretically you are bringing this V to 0. That means theoretically your iron loss is 0. So you are left with only friction and windage loss. That is option D. Next, if you come to question number 158, a three-phase induction motor driving a constant torque load at rated voltage and frequency, both the voltage and frequency as half. Following statement relate the new condition of the stator resistance, rotor reactance and core losses. These are ignored. So these are the statements. The difference between synchronous speed and actual speed remains same. The air gap flux remains same. The stator current remains same. The per unit slip remains same. So if you maintain this V by F ratio, so obviously your air gap flux will remain same, because your flux is E is equal to E is directly proportional to phi into F. So that is phi is directly proportional to V by F. So if you can keep this ratio constant, that means your phi is always constant. So obviously 2 will be one of these, in the option 2 should be there. Then your stator current remains same. Obviously it will remain same because you are drawing constant load torque. Because you are drawing constant load torque, so this one should also be same. Now you see the gap. What should be the gap between synchronous speed and actual speed? Suppose it is running at 1000 rpm and your synchronous speed, and your rotor speed is suppose 950 rpm. So the rotor is cutting, the flux is cutting at the rate of 50 rpm, and accordingly EMF is generated, accordingly your I is generated, current required. Because you are keeping that constant I, torque is constant, so you need to keep that I constant. So what happens? This gap should be maintained. So suppose if you reduce to, because they have done it to half, V is also half frequency. So if frequency is reduced to half, then obviously it will come to 500. So once you are reducing this one is to half, then what should be your rotor speed? Rotor speed, the gap should be of 50 rpm only. Why? Because rotor should cut the flux at 50 rpm only. What is the gap? On that rpm, the rotor cuts the stator, because rest it is rotating. So what is left? It is not rotating. It is rotating, one is rotating 1000 and it is rotating 950. So if it is at 0, so it will be at 50. So if you can think this is at 0, then it is cutting this one at 50 rpm, because it is rotating 50 rpm faster. So the flux should cut at 50 rpm only, so that the EMF should be same, E2 should be same, so that your I should also be same, because you are going for constant torque. So that's why the gap should be same. So if your gap is same, that means option 1 is also correct. Now if you think it now for the per unit slip, what is the per unit slip here? 50 by 1000. What is per unit slip by 50 by 500? So obviously per unit values are not same, because the base is changed, synchronous speed is changed. So 4 is not the answer. So it is 1, 2, 3. That is your option B. Now if you come to question number 159, an AC induction motor is used for speed control application. It is driven from an inverter with a constant V by F. The motor nameplate is given. Number of poles V, P, and the motor is run with an inverter output frequency set as 40 Hz with half the rated slip. Now slip you have reduced it. Now what is the original slip? Let me calculate, because they have given 2850. I can calculate NS also. So what is my NS? NS is 120 into F is 50 by pole is 2. So it is 3000 rpm. So what is rated split? It is 3000 minus 2850 divided by 3000 into 100 in terms of percentage. So it is 153. So it is 5%. Okay. Now your synchronous speed will be equal to 120 into, because you are rotating it now, you are given at 40 Hz. So it will be 40 by 2, 2400. Now what is your slip dash? S dash is not 5%, because it is at rated half the rated slip. So it will be 2.5%, that is 0.025. So what will be your new speed? NR will be equal to 1 minus S 0.025 into 2400. That will be equal to 2340 rpm. That is your option C. If you come to question number 160, what they are asking here, the direction of rotation of three-phase induction motor is clockwise when it is supplied a three-phase sinusoidal having a phase sequence ABC for a counterclockwise rotation. So you have to change this sequence. It is A, it is B, it is C. So it is clockwise sequence. So you see which one is changed in which option. It is next is first option is BCA. So BCA, it is same clockwise, so it will not change. It is the same phase sequence. CAB, it is also clockwise, CAB. So that will also be same. ACB, ACB is counterclockwise, you can see. ABC was clockwise, now ACB is counterclockwise. So obviously option C is the correct option. D is not. Both these are same phase sequence like ABC. ABC, BCA is same because it is clockwise. Only there are two sequences. One is clockwise sequence, one is anti-clockwise. You have to see which direction it is. So that's why it is option C. You have to change the direction, you have to change the phase sequence. If you like the video, then press the like button and please give your valuable comments in the comment section.